Since 2022, astronomers have been picking up something in the depths of our own galaxy that shouldn't, by most existing physics, be possible. Bright, powerful bursts of radio waves, repeating over and over at intervals ranging from a few minutes to several hours, some pulsing steadily for more than 30 years, others switching on and off unpredictably, one or two going permanently silent after being found. Only a dozen of these strange sources have ever been detected anywhere in the sky, and for most of them, scientists genuinely didn't know what was producing them. It's not an exaggeration for dramatic effect. The leading, most established explanation for repeating radio signals in space, a rapidly spinning dead star called a neutron star, runs into a real physics problem here. Neutron stars are supposed to slow down as they age, and once they slow down enough, the physics says they should simply stop producing radio emissions altogether. But these mysterious signals were repeating on timescales of minutes to hours, thousands of times slower than any neutron star should be able to pulse and still shine in radio waves. Something didn't add up. In June 2026, an international team of astronomers, led by a PhD student in Australia, finally cracked one piece of this puzzle wide open, not by solving it in theory, but by catching one of these signals in the act, across multiple types of telescopes simultaneously, and tracing it back to an actual, physical, verifiable source. They're calling it a Rosetta Stone, a reference point that, for the first time, gives scientists a real physical system to measure every other unexplained signal against. By the end of this video, you'll understand exactly what these mysterious signals are, why they broke a fundamental rule of astrophysics, what astronomers actually found this time, and why, even with this breakthrough, most of these strange cosmic clocks are still completely unexplained. To be upfront from the start, this video isn't going to tell you every mystery in this field just got solved, because it didn't. What it will give you is a clear, honest picture of the one genuine breakthrough that did happen, exactly what it proves, and exactly where the boundary of current knowledge still sits. To understand why this discovery matters so much, you first need to understand exactly what makes this class of signal so strange in the first place, and why it stumped astronomers for years. Scientists call these signals long-period radio transients, or LPTs for short. And it's worth being precise about what that actually means, because it's easy to confuse them with a different, more famous phenomenon called fast radio bursts, or FRBs. FRBs, first discovered back in 2007, are extremely brief, lasting only milliseconds. Most of them come from galaxies far beyond our own. They've generated their own decades-long mystery, with theories ranging from magnetars to, in the earliest days of speculation, even some fringe suggestions of artificial origin before mainstream astrophysical explanations took hold. Long-period radio transients are a completely different animal. They repeat on timescales of minutes to hours rather than milliseconds, and the ones discovered so far all sit within our own Milky Way galaxy. The two phenomena share a superficial similarity, and both involve unexpected radio bursts from space, but the physics behind them and the mystery surrounding each are genuinely distinct. The first long-period radio transient was discovered in 2022, an object designated GPM J183.910, found essentially by accident, using radio telescopes designed to scan huge portions of the sky at once. It repeated its bursts roughly every 22 minutes. A period so long that if it really was a spinning neutron star, it would be spinning far, far slower than physics says should still allow it to emit radio waves. Neutron stars work like cosmic lighthouses. As they spin, beams of radiation sweep across space and we detect a pulse each time that beam crosses our line of sight. That lighthouse mechanism is exactly how ordinary pulsars, rapidly rotating neutron stars discovered back in 1967, have been understood and studied for nearly 60 years, typically spinning and pulsing anywhere from several times per second to once every few seconds. But a neutron star's radio emission depends on how fast it's spinning and how strong its magnetic field is. And there's a well-established boundary in astrophysics, sometimes called the pulsar deathline, beyond which a neutron star should be spinning too slowly to produce detectable radio emission through that mechanism at all. Objects pulsing every 20 minutes, or in more extreme cases, every couple of hours, sit far on the wrong side of that boundaries, not just slightly outside the expected range, but by orders of magnitude. Under standard neutron star physics, they simply shouldn't be lighting up in radio waves the way they clearly are. That contradiction sent astronomers scrambling for alternative explanations. Some proposed exotic, highly magnetized neutron stars called magnetars, operating through mechanisms not yet fully understood, might be capable of producing these signals despite the usual rules. Others proposed something entirely different: white dwarfs, the dense, Earth-sized remnants left behind after smaller sun-like stars die, paired up in close binary systems with a companion star, where interactions between magnetic fields and stolen stellar material might generate the observed pulses through a completely different physical process than anything happening inside a neutron star. For years, Both explanations remained live possibilities, and different long-period transients seemed to hint at different answers, without any single confirmed case clean enough to settle the argument definitively. That's exactly the gap the June 2026 discovery was designed to close. In a paper published in the journal Nature Astronomy on June 1, 2026, an international research team led by Covey Rose, a PhD student at the University of Sydney working with Australia's National Science Agency, CSIRO, reported the clearest, most complete case yet. A long-period radio transient called ASCAP J17455051, whose exact source they were able to identify with genuine confidence for the first time. The object was originally detected using ASCAP, the Australian Square Kilometre Array Pathfinder, a radio telescope located at a remote site in Western Australia on Wajarri Yamaji country, officially named Inyarimanha Ilgari Bundara. ASCAP is specifically designed to combine a wide field of view with high resolution and exceptional sensitivity, which makes it unusually well suited to catching unusual, easily missed signals like these across enormous swaths of sky at once. Once ASCAP flagged the signal, the research team brought in an extraordinary array of additional instruments to study it from every possible angle. Follow-up observations came from Australia's own Australia Telescope Compact Array, the Meerkat radio telescope in South Africa, the SOAR and Magellan optical telescopes in Chile, and 2 dedicated X-ray and ultraviolet space observatories, NASA's Swift Observatory and the newer Einstein probe. Researchers from 6 countries, Australia, the United States, China, Canada, Spain, and Israel, contributed to the final analysis. That's an extraordinary amount of coordinated observational effort dedicated to a single faint signal, and it's exactly that combination of instruments that made this discovery so much more conclusive than previous attempts to identify similar objects. Each instrument contributed a different, essential piece of the puzzle. Radio observations from ASCAP, the Australia Telescope Compact Array, and Meerkat captured the precise timing and polarization of the repeating pulses themselves. The optical telescopes in Chile, SOAR, and Magellan allowed researchers to capture a detailed spectrum of light from the system, revealing the specific chemical fingerprints, strong hydrogen and helium emission lines, that identify exactly what kind of stars are actually present. And the space-based Swift and Einstein probe observatories supplied the X-ray data needed to confirm that high-energy emission was happening on the same clock as the radio bursts. No single one of these observations on its own would have been enough to confirm the system's true nature. It was only by combining radio, optical, ultraviolet, and X-ray data gathered by telescopes on 2 continents and in orbit that the full picture came into focus. Here's what they found. ASCAP J17455051 turned out to be not a single dying star, but a pair of them locked in an extraordinarily tight orbital dance. One is a white dwarf, the dense, burnt-out core left behind after a sun-like star exhausts its fuel, roughly the size of Earth, but carrying a mass close to that of our entire sun. Its companion is a red dwarf, a smaller, cooler, less massive star, containing only about 1/10 the sun's mass. These 2 stars orbit each other so closely that they complete an entire circuit in just over an hour, meaning if you could somehow watch the system from a stable vantage point, you'd see one star complete a full lap around the other, roughly 24 times in the span of a single Earth day. That extreme closeness is the key to the entire mystery. The white dwarf's gravity is strong enough to actively pull material directly off its smaller companion star, in a process astronomers call accretion. As that stolen gas spirals inward toward the white dwarf, it heats up dramatically, releasing bursts of X-ray light. At the same time, the interaction between the 2 stars' powerful magnetic fields, each many thousands of times stronger than the magnetic field inside a hospital MRI machine, generates the pulsed radio emission that first caught astronomers' attention. Both effects repeat on the same underlying clock, the system's orbital period of roughly 4 hours. Crucially, when researchers compared the timing of the radio bursts against the X-ray bursts in detail, they noticed something subtle but scientifically important. The 2 signals don't peak at exactly the same moment in each orbit. As Rose explained, that timing difference reveals that the radio and X-ray emissions are actually being generated in physically different regions of the system. The X-rays coming from where infalling gas crashes into the white dwarf's surface, and the radio bursts coming from a separate process involving the interacting magnetic fields elsewhere in the system. Untangling that distinction required precisely synchronized, multi-wavelength observations that simply hadn't been available for any previous long-period transient with this level of detail. To understand why this particular discovery earned such a specific, memorable nickname, it helps to understand exactly what the original Rosetta Stone actually did. The real Rosetta Stone, discovered in Egypt in 1799, contained the same official decree written out in 3 different scripts: Egyptian hieroglyphics, a simpler Egyptian script called Demotic, and ancient Greek. Because scholars could already read the Greek, Having the exact same message repeated in hieroglyphics right alongside it gave them the missing key they needed to finally decode a writing system that had been unreadable for over 1,000 years. It wasn't that the stone solved every remaining Egyptian mystery on its own. It gave researchers a reliable reference point, a known translation they could use to work out the rules for everything else. ASCAP J1745 5051 functions almost exactly the same way for long-period radio transients. As Rose put it, this system gives astronomers a way to decode these signals, a means of determining whether other unexplained long-period transients are more likely to behave like slowly spinning neutron stars or like accreting white dwarf binaries, essentially acting as a stellar Rosetta Stone for the entire mysterious class of objects. Here's why that comparison genuinely holds up, rather than being just a catchy science communication phrase. Before this discovery, researchers had two competing theoretical frameworks: the neutron star hypothesis and the white dwarf binary hypothesis, but no single object confirmed clearly enough, with enough independent simultaneous evidence, to serve as a solid reference case for either one. ASCAP J1745 5051 changes that specifically for the white dwarf side of the argument, because researchers were able to directly observe the optical spectrum of the system, revealing strong hydrogen and helium emission lines characteristic of exactly this kind of accreting binary. Combined with precisely timed radio and X-ray data lining up with a measured orbital period, this case moves from theoretical speculation to a confirmed, physically understood system. Now, when astronomers find a new, unexplained long-period transient anywhere else in the galaxy, they have an actual verified example of what a white dwarf binary explanation should look like across every wavelength of light, which they can directly compare the new signal against. That comparison capability matters enormously because these systems also offer something astronomers can't easily get anywhere else: genuine natural laboratories for studying extreme physics, the magnetic fields, the accretion process, the intense gravitational interactions happening in a system this compact and this violent simply can't be recreated inside any laboratory here on Earth. Every confirmed system like ASCAP J1745 5051 gives physicists a real, observable testbed for theories about how matter and magnetic fields behave under conditions far more extreme than anything in our own solar system. It's also worth noting just how significant the X-ray detection specifically was. ASCAP J1745 5051 is only the third long-period radio transient ever confirmed to emit X-rays at all, following two previous cases. And it's the very first one where researchers have been able to confirm exactly why those X-ray bursts repeat on such a precise, predictable cycle. That combination, a confirmed physical mechanism tied to a measured orbital period, backed by simultaneous multi-wavelength data, is precisely what elevates this from simply one more weird signal to a genuine reference point the entire field can build on. There's also a broader scientific value here that goes beyond simply naming what this one object is. Cataclysmic variable systems, the broader category of accreting white dwarf binaries that ASCAP J1745 5051 belongs to, have actually been studied by astronomers for decades in other contexts, well before long-period radio transients were ever discovered. What makes this specific case new and valuable isn't the existence of the white dwarf binary itself, but the confirmation that this already well-understood type of system can also produce the specific kind of long-period, coherent radio pulsing that had previously only been associated with the neutron star mystery. That connection, linking a well-studied stellar phenomenon to a previously unexplained one, is exactly the kind of bridge that turns a strange anomaly into a genuinely understood piece of astrophysics. Here's where it's important to be honest about exactly what this discovery does and does not accomplish, because the researchers themselves have been careful and explicit about the limits of their own conclusion. Covey-Rose and his colleagues have been clear that this result does not solve the mystery of long-period radio transients as a whole. It confirms one specific system as a white dwarf binary, with strong multi-wavelength evidence behind that conclusion. But out of the roughly dozen long-period transients discovered since 2022, only a small handful have been confirmed with this level of certainty at all, meaning the physical origin of most objects in this class remains genuinely, scientifically unresolved. The clearest example of just how unfinished this picture still is comes from a different long-period transient called ASCAP J8320911. In a separate paper published in Nature in 2025, researchers reported radio and X-ray emission from that object repeating on a 44, 2-minute cycle, but with properties that, according to the researchers who studied it, don't match any previously known type of object in our galaxy. Some scientists have proposed it might be an unusual kind of magnetar. Others have suggested white dwarf accretion, magnetic interaction between two compact objects, or possibly some other mechanism entirely that hasn't been fully worked out yet. Unlike ASCAP J17455051, this object has not been definitively pinned down, and it remains a genuinely open question in the scientific literature. That's precisely why researchers describe long-period transients as likely having more than one type of origin, rather than a single universal explanation. Some may turn out to be white dwarf binaries, similar to the newly confirmed reference case. Others may genuinely be exotic, slowly rotating neutron stars, behaving in ways current physics doesn't fully predict. And some may turn out to be something else altogether, a type of object nobody has properly categorized yet. Rose himself has said the team is only just beginning to understand this entire new class of cosmic events, with each new confirmed case helping piece together a larger, still incomplete picture. There's an added layer of difficulty in resolving the remaining cases, too. Many long-period transients have been discovered close to the dense, dusty central region of our own galaxy, where thick clouds of interstellar gas and dust make it extremely difficult to gather the kind of detailed optical spectroscopy that helped confirm ASCAP J17455051's true nature. Without a clear optical spectrum, researchers lose one of their most powerful tools for directly identifying what kind of stars are actually present in a given system, which is part of why so many of these objects remain stuck in observational limbo, detected only in radio waves, with their true physical nature still essentially guesswork. That honesty is exactly what makes this a genuinely credible scientific story, rather than an overstated one. The Rosetta Stone isn't being presented as a solution to the whole mystery. It's being presented as the first reliable translation key for one part of a much larger, still partially unreadable text. So here's where this genuinely stands right now. Since 2022, astronomers have detected around a dozen long-period radio transients. Mysterious, slowly repeating radio, and sometimes X-ray signals from deep within our own galaxy, several of which appear to directly contradict established physics about how neutron stars are supposed to behave. In June 2026, an international team led by Covey Rose confirmed for the first time with this level of certainty that at least one of these objects, ASCAP J17455051, is an accreting white dwarf binary, a tightly orbiting pair of dead and dying stars, one of them siphoning material from the other, generating radio and X-ray bursts on a precise 4-hour cycle. It's a genuine scientific breakthrough, confirmed across multiple independent telescopes and wavelengths of light, and it now gives astronomers a real reference point for decoding similar signals elsewhere. But most of the roughly dozen known long-period transients still don't have a confirmed explanation. Objects like ASCAP J18320911 remain genuinely mysterious, displaying properties that don't cleanly fit any established category of astronomical object. Whether those remaining cases turn out to be more white dwarf binaries like this newly confirmed one, exotic, slow-spinning neutron stars nobody has fully explained yet, or something science hasn't properly categorized at all, is still an open question that researchers are actively working to answer. The real question isn't whether space still has genuine, unexplained mysteries left in it. It clearly does. A dozen strange, ticking cosmic clocks, most of them still unexplained, sitting scattered across our own galaxy. The real question is how many of them turn out to share the same origin as ASCAP J17455051, and how many are hiding something science hasn't discovered yet. If you want to be here, the moment astronomers confirm the origin of the next long-period transient, or finally crack the mystery of objects like ASCAP J18320911, subscribe to the channel and turn on notifications, because when that update lands, we'll break it down here with the real data, not the invented version. One signal, one confirmed answer, a dozen mysteries, most of them still unsolved. Whatever gets discovered next in this field, this moment, June 2026, with one confirmed reference system in hand, and roughly a dozen others still waiting to be decoded, marks the point where long-period radio transients stopped being a single, undifferentiated mystery and started becoming a genuine area of astrophysics, with at least one confirmed answer to compare everything else against. Thanks for watching.